these gigantic gas clouds at the beginning have a mass which is, it's 10,000 to 1,000,000 times the mass of the Sun. Now, the mass of the Sun is 2 times 10 to the 30 kilograms. That's a 2 with 30 zeros after it. That's a lot of kilograms. And so, it's kind of hard to imagine. So, well, I thought, well, if there is okay, so if the mass of the cloud is 1,000,000 times the mass of the Sun, well, that's 2 times 10 to the 36 kilograms, and that's a bunch of particles. That's like 6 times 10 to the 62 particles in this cloud. And that's an even worse number, and I thought, I'm going in the wrong direction. This is getting even worse. So I thought, well, how many particles is there in a person? Because that's something we can relate to. At least, you know, everyone brought their particles tonight, which is great. So, you know, give or take a few particles. We're talking about 4 times 10 to the 27 particles in a person. 4 with 27 zeros after it. That's a lot of particles. Good job. Good job bringing your particles tonight. But that's still a lot less than the total number of particles in this cloud. And I thought, how can I possibly compare the number of particles in a person to the number of particles in a cloud? Well, this is the best I can come up with. If you took the number of particles in a person, if you took a person, and if you had a lot of people, we're going to need a lot of people. If you took a person and put that person on every single star in the universe, so we're talking about 1 times 10 to the 22nd stars, every single star, every solar system, every galaxy, every universe that we can see in the observable universe, you would still have less particles than the number of particles in one giant molecular cloud. I think that's pretty neat. Obviously, all of these particles don't end up going into stars. And this is how the two forces of gravity and pressure actually are pretty good for explaining how this works. Now, I'm actually going to use this slide for the rest of my talk. I found that any concept in physics can actually be explained by the use of a spring and a bowling ball. That's not true. That's not quite true. I'm actually going to use a pulley as well. So anyone who's taken first year physics, you know what I'm talking about. Okay, so I hope that I've convinced you that these clouds are gigantic and that they have a lot of particles and they have a lot of potential to make clouds. Well, how then do they make stars? You have a cloud sitting out there in a galaxy, the universe is just sitting there. Well, the particles in that cloud have some energy. They have kinetic energy. And that stops the cloud from collapsing because the particles are moving around. They have gas pressure. This is a gas cloud. A gas is just another fluid. So the particles are bumping into each other. They're randomizing their motion. They're moving all over the place. And that stops it from collapsing. But an amazing thing happens if you have a certain mass. Now, I'm not going to show you the equation. I'm just going to talk about it. It doesn't really matter. It totally depends on the orientation of the cloud, on the density that you start with. But what happens is that if you cross over a critical mass density, all of a sudden something incredible happens. And that is that gravity figures out, hang on a minute, I can pull this stuff together. I can take these particles over here, and I can take these particles over here, and I can condense them. I can start them to collapse. And the mass that we talk about is actually called the Jeans mass, after the guy who invented this, well, observed it, he didn't invent it, it was happening before he was born. So, if you have a certain mass, the cloud all of a sudden realizes that it has slight inconsistencies in its density. And all of a sudden, these points of slightly higher density start to pull on the matter around them. And you start to get fragmentation of the cloud. So that's how one gigantic cloud doesn't just turn into one gigantic star. Because little parts of the cloud collapse at different rates and with different potentials. So, in the end, what you're going to get once you have this collapse, once you have all of these little pockets of stars created all over the place, you know, stars which are much, much larger than the Sun, which is 2 times 10 to the 30 kilograms. Some stars are up to 60 or 70 times as massive as the Sun. Some stars actually have less than 10% of the mass of the Sun. It's amazing. But what happens is that if you get to high enough density, you have high enough temperature, and all of a sudden, something even more incredible happens. It's not incredible, it's just really neat. I shouldn't say incredible. Nuclear fusion. Until this point, all of that material, all of the stuff that will end up being stars, is exactly like the gas in this room. Slightly different composition. There's nothing special about it. It starts off with a density much lower than the air in this room, which I think is kind of neat. Once you get enough of it together though, and we're talking about a lot, you can push the atoms close enough together that they start fusing, you end up with the second most powerful effect in the universe, nuclear fusion. The power that fuels every single star. Which is really neat. Until recently, I thought this was the most powerful force in the universe. I went to a professor and I said, but I can't believe that this is not the most powerful. And they said, well, what are you talking about? You should have learned that in kindergarten. I didn't go to kindergarten in America. You know, like this is, obviously I should have picked this up. You learned that, right, Desiree? Yeah. This is the problem of being an international student, apart from the accent, which is so difficult. So, why do I have, the bowling ball should be obvious, right? The bowling ball is, of course, a gravity, the bowling ball is pulling all this mass together. Why do I have the spring? Well, that's the gas pressure holding up the star. That's stopping the star from collapsing to a single point, to a singularity. I shouldn't say that, I'm not talking about black holes, but every star has a certain radius, right? Every star has a certain volume, and that's because of the equalizing force of its pressure, of its gas, that's holding the star up under the collapse of gravity. So, I realize that I've just spent a few minutes talking about this, but, well, I've got a surprise for you. I actually have a movie, which is kind of neat. And what you can see here is exactly what I've been talking about. Fragmentation of the cloud, small pockets growing in density, those densities getting higher and higher, increasing their temperature, and finally, although it's very quick in this movie because it's very speeded up, crossing over the threshold for fusion, and baby stars are born. Another word for this is a stellar nursery. It's kind of neat. Little cute, baby stars, incredibly violent, very difficult to form planets around, but quite neat. So as you can see, the material, once you form a star, can still accrete onto the surface. It can still come down and be attracted by the star's gravity at an incredible rate. And you can see that the stars themselves are interacting in these clouds. And in fact, that's how stars like our sun actually got ejected from the cloud that they were born in. Because pretty much all stars are born in a situation like this. And it's incredibly dynamic. It's amazing. I really think that it's incredible. Of course, pretty much all of the stars that you can see in this movie are big stars. And they form much quicker than little stars. And that's okay. Okay. Alright, so once you have stars being formed in their molecular cloud, once you have stars being ejected, once you have the onset of fusion, you get to a point of what we call the zero-age main sequence. You get to the point where the stars, dependent on their mass, have started to burn hydrogen in their cores. I say dependent on their mass because the heavier a star is, the bluer it is, the hotter it burns, the quicker it burns through its material. So, bigger stars, and when we say bigger stars, we're really talking about blue stars, the sort of stars that form black holes and things like that. Not the sort of stars that I'm going to be talking about tonight. Yeah, they don't live as long. They don't live as long as the stars that we're going to be especially interested in tonight. The sort of stars that end up in cataclysmic variables, which is what I'm particularly interested in talking about. This is actually a picture. I'm not going to explain this picture. This picture is